So as the slide said, and as Bistra said, I'm from IPAM Research. I'm also, by the way, research associate at the Technion, the Faculty of Decision and Data Science. And what I've been doing throughout my career is trying to help enterprises make better decisions using mathematical techniques such as optimization. And today what I'm going to talk about is democratizing optimization. And so first I want to explain what the issue is that this body of research is trying to address. So as we all know in this room, optimization can bring very significant benefits to a large number of enterprises in many domains across many use cases. These are just some examples from the Edelman competition, the Informs Edelman competition. I think this is actually pretty outdated, showing all the variety of use cases and the benefits that were achieved from them, sometimes in the millions of billions of dollars. There are also, as we all know, some other societal benefits, some other applications where optimization has been applied, such as chemotherapy treatment, which is also one of the Edelman winners, and so on. So definitely, optimization can bring a lot of value in many cases to many enterprises. But in order for this value to be realized, it requires creating an optimization model. This usually starts with a business person specifying the problem to be addressed in some form of natural language. It's actually pretty structured. What appears here, this is typically what you get after several iterations of refinement with a business person trying to explain and understand the problem, so you can break it down to the core components. So, for example, a model required to determine the order of custom computers we processed on an assembly line. Once the order is assigned is kept from start to finish. Notice there's a sort of a constraint embedded here. Custom computers, different lists. Additional constraints here, minimum number of computers, and so on, up and bound number of computers. And so this is just one example, again, of a problem definition that to which optimization can be applied. And then the next step is for our optimization modeler to take this definition and translate it into some formal statement that can be actually solved. And one way to do this is use an optimization modeling language. This is what appears here is in OPL. IBM's modeling language, but of course there are other modeling languages as well, in which in this case, the optimization model is declaratively defined, given a set of inputs, and once combined with a specific set of inputs, a specific instance of optimization problem is created and can then be solved by, in this case, a mixed integer linear programming solver. And so formally, the optimization model can be specified in this way. This is actually very similar to what we saw earlier. Basically, there's an objective function that in this case needs to be minimized. We want to find a solution that minimizes this objective function, but the solution also has a set of constraints. And notice that in this case, both the objective function and the constraints are parameterized by the set of inputs, because this actually defines a set of optimization problems, and only once the set of a specific input has been given, then the optimization model can be solved and a solution can be given. So all this process has to be carried out in order for optimization to be applied to a problem. And so the current process, if thinking what actually breaking down further into a set of steps and how this actually works, so we have the business user on the one side, that's both the person that defines the problem in business terms and is then the user of the system. We have the optimization modeler. They have to work together. And what has to be carried out are the following steps. So the business problem has to be understood by the optimization modeler. So this has to be done together. Then the optimization modeler, and this is the current process, creates a formal model of the optimization problem. Then this, for example, this more structured natural language that I showed earlier, this needs to be then translated into an actual optimization model that can be executed, may need to be broken down, decomposed, and so on. There are a lengthy number of steps that may need to be carried out here. Models need to be chosen, and so on. Then it needs to be tuned for efficiency so that it can be solved and given some useful output. Now, just a caveat here, so we all know, as was mentioned, we all know these problems in many cases are NP hard, they're very large scale. The good thing working for us in practice is that typically you don't need to come up with an optimal solution, you need to come up with a solution that's significantly better than what the human user can come up with on their own. And then, again, this is the current practice. Only after all the modeling steps have been carried out, tuned for efficient, and the model starts generating out solutions, only then can typically the user, then comes back to the business user, can then start checking and testing whether the solution is actually, whether the model actually captures what the user intended, whether the results are reasonable, whether maybe a constraint has been forgotten and the results are completely unusable, in which case this process, several iterations we need to go. Of course, subsequent iterations typically take less time than the first set of iterations. And this is a very significant problem in applying optimization in practice, because what happens, first, it's not always easy to convince business users to even use optimization, because a reaction we often get is, no model is going to do a better job than me with my 30 years of experience working this system. But even, so we say, okay, let us prove it to you. And so we work and we convince, okay, let us prove it to you, and say, okay, what's it going to take for you to prove it to us? So, and then it comes down to say, okay, we need to go through this process. This is a very lengthy process. You need to commit some time. You need to commit time. You need to invest money, because these people, the optimization modelers, they don't work for free. They're going to be investing their time as well, and so it becomes a very significant hurdle to actually applying optimization in practice. And this is the problem that we're trying to address, as I said, with this body of research. So if I were to sort of a very rough sketch or breakdown of how how such problems could be solved. So there are several techniques, and of course I may have missed some out, but a very rough sketch. So the first is creating a custom algorithm for a problem. Now, of course, this is the best in terms of being tuned for the specific problem. It often gives the best solution. Once a good model is created, it often gives the best solution in terms of objective functions and so on. But it's the most difficult to create because it requires creating very custom code. And it's also very difficult to customize, because if you need to add a constraint, often this is very custom code to the specific problem. You need to add a constraint. You need to change a lot of the underlying code and work. But this is often typically reserved for sort of the core problems of the business. This is, for example, think of a shipping company like UPS that has to optimize their shipping routes, or so they often have their in-house OR team that for these types of problems, that's what they, a large part of the work consists of creating such custom models for the core business. So this is very limited in its scalability to how widely this can be applied in practice. The next step is mathematical programming. This is creating a model in such a mathematical programming language like the one I showed earlier. Now, this is very good because it has theoretical guarantees, provides an optimality gap, and it's typically the first model that you create is not too bad, and when you tune it correctly, it's extremely efficient. And when the proper cuts are applied, heuristics and so on. But it requires, by tuning it to the specific problem and breaking it down, thinking how it can be created using techniques such as mixed integer linear, how to linearize the constraints and so on, again, requires significant optimization expertise, even for the initial modeling, initial model creation. So that's the downside. Then there are meta-heuristics. Meta-heuristics, in my view, they're deceptively simple in the sense that they're often presented as almost any computer programmer can create or solve a model and solve an optimization problem. But so it's very easy to create something very quickly that actually runs, that takes an input and runs and is even mathematically correct. But the issue is that unless the meta-heuristic is specifically tuned for the problem, the solutions you get are much worse than even randomly generated solutions or something that the user could have done anyway. So often what happens, again, if this is incorrectly used, is that it gives the impression that something is, that optimization is not good, because the impression the user gets, yes, we tried to apply the optimization, but optimization couldn't find any good solution. So, so it's useless. We shouldn't try it again. So it's very interesting, of course. But when correctly tuned, it can be significantly more efficient than mixed integer linear programming for some discrete, from some classes of discrete optimization problems like vehicle routing. So there definitely is a place for it, but it needs to be, in my view, very carefully used and used appropriately. And of course, there's the additional issue that there's no theoretical optimality gap. It's very hard to know how far away you are from the optimum, but it's very good at providing good solutions if tuned appropriately. And then there's this final item that appears here, which is Markov decision process or reinforcement learning. What I like about this paradigm is that it abstracts away a lot of the details. It sort of requires a thought shift in the sense that the user or the problem needs to be thought in terms of states and actions and rewards rather than other aspects. It also means that this is only suitable for sequential, or not only, but typically it's most suitable for sequential decision-making problems. Of course, it can be, in many cases, can be rolled out. But there is either the curse of dimensionality, if you want to use Markov decision process, the linear programming, or extensive hyperparameter and algorithmic tuning, again, requires a lot of expertise. And there are additional difficulties, such as incorporating the types of constraints that are often present in business problems. So this is sort of the standard practice or standard state of the art in applying optimization to solving business problems. And what we've been working on is how we can take AI and simplify this process. And what I hope to convince you is in the next couple of slides is that due to a large body of work, definitely not just by ourselves, but by many people, almost everyone here and others in the world, AI can already significantly simplify the model creation, but it sort of shifts where the focus needs to be placed in order to enable closing this end-to-end loop of creating an optimization model. And so let me start with, and I'll give you two concrete examples of that. One, which is something that's going on for a couple of years, which is constraint learning. So I don't know how familiar you are with constraint learning. So let me explain to you where constraint learning is useful. So constraint learning is useful even in cases where it's very difficult to model the explicit constraints. Think of a very complex dynamic system, or I'll give you another example later on, where it's either very difficult to create a model of some of the constraints or some of the objectives. And if data is available, but the data that needs to be available here is the historical uncontrollable, these are the parameters that I mentioned, and also historical decisions that were made, right? And the objective and constraint outcome, if such data is available. In many cases, such data is available. Again, think of, in this case, a large chemical process plant, right? So the plant is already operating. They didn't sit on their hands and wait for us clever people from the optimization space to come and give them a model before they start operating the plant. The plant is already operating. They've already made decisions. They have sensors. They can capture this data. So in this case, what constraint learning says, okay, let's take this data. Let's create some model, machine-learned model of this system, okay? And then for some types of models, there are already techniques for embedding it into mixed integer linear programming model. For example, think of a deep deep learning network with ReLU activation functions. These can be very simply transformed into mixed integer linear. Of course, there's a limit on the size of the network and so on. So, but in principle, this can be translated. But so
I found this on the web.
Sorry. So, but the issue is here that, okay, so we took this, we learned it, but we learned across decisions that were made historically. And now we're using this in an optimization model, right, that actually now shifts the decision, trying to shift the decision to maybe a completely different space. So this flies in the face of the base assumption of machine learning that the test or the data that we want to test our model on is from the same distribution, because the optimization model actually completely shifted or may have completely shifted distribution of where the decision is, because typically the decisions we have is, based on rules of thumb, what users did and so on. And so this model could be very inaccurate in the space where the decision is being generated. Let me give you now a concrete problem, which I also used to illustrate, a concrete optimization problem, which I'll use to illustrate. It's taken from this reference later on. So think of a problem of providing an optimal food basket to a third world, to developing countries. Okay, so we have an objective which is minimize cost. This we can write down explicitly. Okay, we have constraints such as nutritional decomposition. So given a food basket, it's very easy to calculate protein and carbohydrate and so on, composition and so on. So that's all well and good. And so of course we want to provide the minimum food that gives the required nutritional components. But there's an additional requirement, which is palatability. How palatable, how tasty it is. Will people actually be willing to eat this, or will it taste so bad that no one will be willing to eat it at all? So how can we model this? It's really unclear. So in this case, and this is what was done in this work, is a regression function using data from historical baskets was used to create a palatability score, and then a constraint is added that this learned regression function needs to be greater than some threshold. So that's the way this was handled. Then you add this to the model, and you solve a mixed integer linear program. That's the approach. So if we were to formalize this problem, what we have is sort of an actual ground truth optimization formulation. We have the actual feasibility set and objective function, and we want to find the optimal solution for this in this setting. But what we actually have is this data-driven optimization formulation. So we have this set of data. The set of data resulted in a approximate either feasibility set or objective function, or maybe even both. Okay. We then take this, what we're actually doing, we're taking this and solving this and finding an optimal solution. So after feeding in this additional parameters, this is what we can get using this technique. And the question that we want to address is, how can we ensure that what we got is a good solution for the actual problem? And I'll define good in a while. Okay, so this is one example of how using AI shifts the problem. So now the problem, notice, changes from creating the constraints for the part of the model which was very hard to model, to one of, okay, I have a surrogate constraint. How can I check that the results that I get are good enough in the actual world, in the real world? Okay. The second, and this is much more frequent, this I played around with Chat GPT. So again, think of a world where a business user doesn't need an optimization expert, can come to a machine learning model and say, okay, I have this problem, can you help me? Can you create an OPL optimization problem for vehicle routing? Okay, of course, the user will need to be much more detailed, but this is what I did. And actually, I was pretty astounded by the results. I don't know how many of you have tried this out, because what ChatGPT returned, it said, okay, here is a simple optimization model. This is what it gives. It doesn't just give the model, it also gives an explanation. This model uses binary decision variables, yi to represent the customized visited, integer decision variables. It looks like a great, like instant modeling, wow. And it doesn't even stop here. because then I say, okay, can you add a constraint saying that all routes should begin and end in a given in a given location? And it says, yes, no problem. To add a constraint that all used, you can use the following code. Again, gives an updated code. It even tells me what it changed in the code to make this happen. Right? See the x start I, x I end, and so on. And so really, wow. I mean, this is amazing. And now I say, wait. I also remember I want to minimize my fuel. And again, no problem. Minimizes fuel consumption, gives the model, gives an explanation. And nice, and it doesn't even stop there because I know what, actually, I want to do some sensitivity analysis. I want to do what happens, what if I can remove the constraint that only customers with demand are visited? Visit anyone you want, not just the customers with demand. And say, okay, here's a version of the optimization model where only customers demand visited, and so I get this. So, wow, so it looks like problem solved, right? But the issue is, how do I know that this model that I get, so think, now this is a business user sitting in front, has no idea about optimization. How can the business user know this model that looks on the face of it great actually models the problem that the actual business problem? Maybe it's a different problem. How can this be validated? And there's also another issue, which is, okay, maybe this is mathematically correct, but can it be solved efficiently, right? I mean, maybe it's a very poor model in terms of efficient solutions, of decomposition. Definitely there are no cuts added here, anything like that for very large problems. It works. So So these are. So it's not that we've solved the problem. Again, this is what I hope these two examples show, but we actually shifted the problem. So we've made these steps now are much easier in today's world, but now these steps become much more prominent in order to close this end-to-end loop. And
So were these models actually correct?
I don't know.
I mean, I'm not sure I recognize the skip the ones that don't have a demand on the last screenshot.
I don't know if the model is correct. I haven't tested it. I think even emphasizes what I'm trying to say, because even for someone who's familiar with optimization, it will take time to check whether it is correct or not, right? And think of it, this is a very simple model, but typically real world models are much larger, maybe decomposed. It's a huge issue. So as I said, I think the problem now shifts to tuning for efficiency and to validate the optimization model. And what I'm going to talk about in the rest of this call is is more on this validation, because I think there's already, and we already saw a significant body of work already in this workshop. I'm going to see more that on how we can address the problem of efficiency, which is using all these great techniques that are already shown for learning to optimize. Adding cuts automatically, doing all those things that were shown, using machine learning and so on. So this is the learning to optimize, but here also I think some additional work may need to be done, because here it's not the optimization expert who is going to be using these tools, but it's going to be the business user. So even here, there's probably additional work, but I'm not going to focus on this. So there's definitely a lot of work here, but I'm not going to focus on this part in my talk. I'm going to talk about model verification or validation. So first, I'm going to show you how we address this problem for the first example that I showed of constraint learning. And then I'm going to talk a little bit about this sort of another approach for closing this end-to-end loop. So just to remind you, the problem of constraint learning. So we have this actual ground truth optimization model. We have this surrogate model, and want to ensure that X is a good solution for the actual problem. So first, how do we define a good solution? All right, so So what's the approach? Before I say how to define the existing solution. So basically what our approach is, we have sort of this box. We want to create this box that we have, that given the set of data, given the surrogate optimization, objective function and constraints, and given a specific input, so we have a specific problem instance, we can measure the quality of the generate optimization solution, how good is the optimization solution created by this surrogate, and augment the optimization model, adding additional constraints so as to meet the required quality threshold, whatever it is. And again, I'm talking very high level because I haven't defined what the quality threshold here and so on. This will become clear in a moment. And then ultimately get a solution. So I'm not going to use the solution generated by this. I'm going to use a solution generated by this augmented optimization model, and this is what I'm going to output to the user. So what we want, so this is sort of the way we would like to define quality. So we would like that first, that the solution that we get from the surrogate model, I see there's a typo here because this should be the actual constraint set, not the surrogate constraint set. We'd like that the solution satisfies the constraint with a high enough probability. That's sort of the first, because we have data, right? So it's probabilistic guarantees. And we would also like the objective on the solution obtained from the surrogate model is close enough, again with a high enough probability, to the optimal solution. That is what we would like. So this we can obtain under some assumptions. This is a little harder. So here we're actually going to relax this and say that what we're actually going to define as a good solution is, so remember I said that in order to have data, you need to have some policy, some way for the system to currently operate. So what we want, so this is this x0, this is how the system is currently operated, or the way currently decisions are being made. We want to ensure that that what we have is an improvement. Okay, it's better in terms of objective value than the way that currently the system is being operated, again with a high enough probability. This is the way we define the quality for the objective function. So again, so we have these two quality measures, probability of constraint satisfaction, probability of improvement, and this is what we want. And if we have this, it's actually not too bad, because then what we can do, we can carry out an iterative process in which we constantly improve the solution that we generate, and at least reach some local minimum of the objective function. Okay, but at least we guarantee that we improve, that we're doing better than what the user is doing. So how do we then calculate this probability of improvement? So the mechanism that we use to calculate probability of improvement is a Gaussian process. A Gaussian process is a way to sort of define uncertainty over a set of functions. So this is how we assume that the uncertainty over the set of objective functions can be captured by a Gaussian process. Of course, we have to select appropriate kernels and so on for this to be valid. And then we want to use the Gaussian process to calculate what we call the probability of improvement, how much we improve. And the way we do that is so we have some prior belief over the set of functions, and given the data points, we can then marginalize and calculate the posterior over the data points of this quantity. So this gives us a mechanism to calculate the probability of improvement, and similarly, using the same modeling, the uncertainty on for example, in the world food palatability that I showed earlier, right, of calculating the food basket over the palatability regression function. If we capture the uncertainty of the regression function using the same Gaussian process, we can calculate the probability of constraint satisfaction or POCS. So this gives us a mechanism to calculate how good a solution is. Yes?
Where do the set of constraints come from? Because you don't know it, right?
Because I don't know. In some case, I don't know. The example that I gave, the palatability. I don't know the actual palatability function. I don't have the actual function that maps a food basket to how palatable it is. I do it with a regression. And I want to check that the actual palatability is above the threshold. What I can check is that the regressed function is above the threshold. And what this gives me is a way to calculate the probability that the actual function is above, that the actual palatability is above the threshold. Okay?
So you would guess the threshold?
No, the threshold is given. In this specific instance, the threshold is given.
So you know the right-hand side?
I know I know the right-hand side in this case. I don't know the left-hand side exactly. Okay, so we have a way to measure. Great. So how do we then augment the optimization model? And I'm not going to go into too many technical details. I can go offline. But but before I do that, let's see how good it is. Okay, so what we did, we generated randomly a set of optimization problems. We assumed the constraint. In this specific case, because we tested the probability of improvement, not the probability of constraint satisfaction, the constraints were given. We learned the objective function, but we had the ground truth, so we could test against it. We also generated some policies. So let me explain this graph. So this is and these are normalized, right? So remember, it's a minimization problem. So the closer to zero it is, the better the initial policy I got is. Okay. So, and the closer to zero this is, the better the solution generated by the constraint learning. Okay, in the actual on-the-ground truth. This is now the initial policy that I got. Each dot, so this dot says that, for example, this dot says that the initial policy that I got was already very good, and also the objective that I got from the constraint learned objective was also very good on the actual ground truth, which I had because I generated this. So and this is and the color indicates how high the probability of improvement here. So what we're seeing is exactly what we want to see. We see that if the if the policy we got is very bad, it's close to 1, right? And then almost everything is indeed recognized as an improvement. And the closer that we get to 0, the better the initial policy is, the less the probability of improvement says that the solution is good. So this is exactly what we wanted to see. And this also gives in terms of false negatives and false positives. So this is where the probability of improvement, this is even for a very low threshold probability of improvement of 0.5. So you can see that we have a very few false positives as rated. This is the false negatives. We have more false negatives, but again, relatively speaking, still a small enough number. And also remember that this problem is biased. We want the error, having a false positive is much more serious than having a false negative, because a false negative says, okay, I couldn't do better than you, keep on doing what you're doing, the way you're currently operating the system. So no harm is being caused. A false positive says, I'm telling you to do something that actually you're going to do worse than what you've done without me. So the probability of improvement is in these experiments turned out to be a very good measure. And now, how do we augment the model? So the way that we augment the model, we use two notions. One we call data sufficiency. So we want to constrain the solution that we get from the surrogate optimization model to be sufficiently close to where we already have data. This is what we call data sufficiency. I'm not formally defining it here, just trying to give the intuition. And we want the model to be sufficiently accurate in the area, again, where the generated solution is. And we want to add these as constraints to the model. So we want to create a surrogate optimization. We want to create an update optimization model where these constraints are added, and we can and these constraints are also tunable, so we can tune how close we are to the existing data set or how accurate it is in order to get the desired probability of improvement. Remember that we have this threshold on how high we want the probability of improvement or probability of constraint satisfaction to be. And also this can be used to enhance trust because the user can, feels more comfortable about actually saying how close it is. And then we solve this updated optimization model, adding these additional constraints. So we have this surrogate model, we add these additional constraints. By the way, these constraints can be formulated as mixed integer linear if the original problem is mixed integer linear. And under some assumptions, this actually can also give us a bound on how far it is from the actual optimum of the system. I can give more details offline. So what we did in order to test this sort of end-to-end, we actually carried out a grid search on the various parameters on the world food palatability problem that I mentioned earlier. Now, what happened there was an implementation in additional paper. There was an implementation where first the world food palatability problem was implemented and tested on various data sets, and there also they recognized the issue that the problem that the generated solution may not be may actually violate the palatability constraint. So what they added the notion of a trust region. They added an additional constraint saying that the solution needs to be in the convex hull of the data, or rather in the convex hull of clusters of the data, assuming that would give a better solution, but there was no formal guarantee. So what we did, we ran, so this is sort of the vanilla implementation. This is the vanilla optimization with a convex hull, with the trust regions, what they call the trust region. And this is the best solution generated by our approach. And as you can see, so first, and this is for varying palatability thresholds. And as you can see, I'm not going to go into all of this because I'm running out of time and I want to cover another topic very quickly. So for a palatability threshold of 0.5, so by the way, in all cases, the vanilla implementation without trust region violated the constraints in all cases that we tested. This is the red region because we needed a 0.5. What we actually got 0.01, 0.09, and so on. For a threshold of 0.5, the trust region indeed managed to fulfill the constraint or satisfy the constraint, but this was the cost, the objective function. So here we managed to satisfy the constraint better, and we got a significantly better objective function than the trust region ones. In all other cases, neither managed to satisfy the constraint, and our approach satisfied the constraints. And in this for 0.6, we not only satisfied the constraint, we also got a better objective function than the trust region approach. And this just emphasized the danger, because without having a formal way to measure, you can see that if they were to go and implement this in the real world, it would have violated the actual palatability constraint. So this is the first work. So any questions before I on to the second? Okay. So now I'm going to talk about an additional work, again with some additional colleagues from IBM, and this is how we sort of put the validation approach or the validation part first to sort of try and close this end-to-end modeling pipeline that I mentioned earlier. So what we want to do, or what we would like to do is actually, this is a very different flow than the one I showed earlier. What we want to do is, what we propose is, we want to understand the business problem, create a verification specification, preferably by the business user. We want the business user to create a specification that it can use to a formal specification of the problem. Then this can be used to check how good it is before creating any model, before needing to run anything, before needing to tune anything or anything like that. And then we want to create, only then do we want to create the optimization model, tune for efficiency, do the final validation, and then again repeat. But here there could be multiple steps, and so we expect this whole end-to-end cycle of model validation, model creation to be much quicker. So how do we do that? So what's a good tool for formal specification that many business users are familiar with? Excel or spreadsheets. And let me show you how we can use spreadsheets as part of this approach. So let's take this example, a very simple example. It can become much more complex very quickly, but I'm going to illustrate using a very simple example. We have an inventory replenishment optimization model, optimization decision. So given a demand forecast, the user wants to find the optimal threshold ordering policy, minimizing lost sales and inventory holding costs. And of course, we need to maintain the quantity conservation. So this bit can begin by a user having the relevant data in the spreadsheet and for the demand forecast over a period of time. Then the business user should be able to, add the cells representing the possible policies, what the lower and upper threshold is, what the initial inventory state is, and the costs, the related costs. And then add the formulas enabling the calculation. So the user can then take this and actually, write the cost for stock out, calculate how I carry over the remaining inventory, the cost per day, how I do the order amount based on the threshold using this if value. All can be done in Excel using very simple formulas. And then you can just copy and paste this across the spreadsheet, and the user already has a tool that they can use to do what-if analysis, validate the constraint, see if it makes sense, play around with the threshold. So here the user inputs these thresholds and get this overall cost across the planning horizon. With this threshold, now the cost is higher and can do a lot of what-if analysis. So this sort of closes the first part of the loop, which given a formal specification and a tool for validation. And then what we want to do is generate an optimization model. And this is where an additional part of our research comes in. How can we take such a spreadsheet-based specification and translate it into an optimization model, optimization formulation? The way we currently, and this is an actual translation carried out, so this just shows this if statement that I showed earlier, how it got translated into a set of constraints. And I'm going to go a little bit more into this. The way we carry this out is we sort of created, you can think of it as a compiler from a spreadsheet to an optimization modeling language using a set of rewrite rules. So the idea is we parse it, we generate, and it goes through a mathematical representation. It sort of captures the underlying knowledge of optimization modeling or optimization specification, and so it has high expressive power, and we use the notion of a set of rewrite rules to take this and progressively move from the Excel or spreadsheet-based specification to the actual optimization modeling approach. So just to give a specific example, so say we have this if statement, which is what I showed earlier in the supply chain. So for example, we can't translate this directly, for example, OPL, because of it doesn't allow things. So we can break this down using the semantics of this if-then-else operator into these two logical statements. This is a rewrite rule. And then using the knowledge that the values are actually integer, because these are quantities, we can then translate this into that either A needs to be less than or equal to B minus 1. Sorry, not either, but A needs to be less than or equal to B minus 1. Because, for example, if you want to translate something to a linear constraint, you can't say smaller than, you can only say smaller or equal to. So that's the way that currently this works. So this, and of course, again, here I haven't addressed the issue of tuning the model. This is where we believe that integration with the work of learning to optimize that was presenting where this comes in. So once the model is created, we use that to solve the model much more efficiently. So to summarize, I hope I've made my case that AI can already significantly simplify the creation of optimization models. I think maybe some of you already believe this coming in, but maybe the more important statement is that this means that we now need to shift our focus to other parts of the end-to-end pipeline in order to actually solve this problem, because it's not that we've solved the problem, we've just sort of shifted the focus, and I presented 2 works on addressing this. And what's next? So the many follow-on works. So for the constraint learning, as I said, what we did grid search. We want to find a much more efficient way to actually find a good set of thresholds, or for finding the augmented model, a much more efficient way. We want to extend, so our current validation first approach works for the rewrite rules, and the compilation works for a small subset of the models, fairly small. We need to extend this if we want to approach. That's one future avenue. Moving forward, another interesting approach, or another interesting way, this I've referred to meteoristic optimizers at the beginning of my talk. I say it's very easy to model, but their learning to optimize is seems to be a much less developed field. If we can enable the models generated by programmers to be efficiently solvable by learning the hyperparameter tuning of the meteoristics efficiently, maybe that's also another good way to close this end-to-end loop. And more maybe far-reaching and contemporary directions are, can we take this, this really amazing ability of describing a problem in natural language and having it translated into an optimization model, but giving the right tools to be able to validate that what is generated is actually a good model? How can we combine the validation and the large language models? Maybe another way is, okay, so I said, okay, we have large language models currently are able to take natural language and translate an optimization model. Can we maybe, for example, take the spreadsheet-based specification and translate this in optimization model? But here we have the added advantage, because the create optimization model can then go back to the Excel and check whether what they generate is actually what was intended, right? So we sort of have this validation built in, but it's not clear how we can then take and update the parameters of the transformer, what would be presumably a transformer-based architecture with attention mechanism, and work back and update the tool. So these are all avenues of research, and that's it. So thank you very much.